Let's look at a technique of differentiation or taking a derivative, and that's what's called implicit differentiation. And this is used, or this technique to take derivatives is used when you have mixed variable terms. Not every time is a function solved for y when you're dealing with equations. So sometimes you have equations that have mixed variables, x and y are together. So in this problem, in this equation, this relationship, we've got x squared y plus 3xy cubed minus x equals 3. And we want to find dy dx. Now, we could solve it for y first, okay, and at times that may not even be possible, or I say possible, anything is possible, but possible to do by hand. But in this case, we're going to use implicit differentiation, which means we're going to take the derivative of everything with respect to x, okay, because again, that's our horizontal when we're talking about the slope of the tangent line or that instantaneous rate of change. It's dy dx. Okay, so I'm going to set it up. I'm taking the derivative with respect to x of each term. So I'm taking the derivative of x squared times y with respect to x. I've got a product here. I'm going to need the product rule. Plus, I've got the derivative with respect to x of 3x y cubed. Again, I'm going to need the product rule there. Minus the derivative with respect to x of x. Okay, taking the power rule for that one. And don't forget, I've got to take the derivative with respect to x of the right side, which in this case is a constant. So that derivative is going to be 0. Okay, so we've got a product rule here. X squared times y. We're going to need 1d2 plus 2d1. So I need 1 times the derivative with respect to x of y, 1d2 plus 2 d1, so this is the derivative with respect to x of x squared, plus, now I need the derivative of the second term, so that's another product rule. So I need 1d2, so 3x is 1, the derivative with respect to x of y cubed, 1d2 plus 2, that's y cubed, times the derivative with respect to x of 3x, minus, now I've got the derivative of x, which is 1 with respect to x, equals the derivative of that constant, in this case it was 3, the derivative of a constant is 0. Okay, so let's organize a little bit. I've got the derivative of this product is my first two terms in the next line. The derivative of the second term, this product, is my next two terms here. And the last terms, the minus 1 and the 0 on the right side, were the simpler derivatives here without any rule, so to speak, other than the power rule. Okay, so operators are here. Operators are in this step. Operators are standing by to tell us what to take the derivative of. So we've got the derivative of y with respect to x. Well, that's dy dx. That's what we're looking for anyway. Plus y, the derivative of x squared with respect to x, is 2x. Plus I've got 3x. Now here is interesting in this one. Taking the derivative of y cubed with respect to x, well, the derivative of y cubed is 3y squared. But very similar to the chain rule, we just took the derivative of something in terms of y and we want it with respect to x. So I need the operator next to it, the dy dx. Okay, next one. Plus y cubed, the derivative of 3x is 3, minus 1 equals 0. Okay, so the only operators I've got now in this line are the dy dx. Everything else, the derivative is done, and in this case, this dy dx, the change in y over change in x here, is what we are looking for. So at this point in this problem, the dy dx is the variable that we're solving for. Okay, so I'm going to move everything that doesn't have a dy dx to the right side. So that means I'm going to keep x squared dy dx plus, I've got this term with the dy dx, so that's going to be 9xy squared dy dx. Everything else is going to the right. So that means I've got the y times 2 times x, or 2xy. When I move it to the right, it becomes negative. I've got a 3y squared on the left. I'm going to move that to the right. That also becomes negative. It's a 3y cubed. I think I said squared. I also have to bring the 1 over. Okay, so now on that left side, I am left with the dy dx terms. I have 2 of them. On the right side, no operators are here. All the derivatives are done. And I've got this expression. Okay, so now I'm going to need to factor out on the left side that dy dx. So now I've got dy dx times a quantity x squared plus 9xy squared. Going to keep that right side the same, minus 2xy minus 3y cubed plus 1. Okay, so from there, I'm going to divide by this binomial, which is acting as a coefficient for the dy dx. So that means that dy dx is going to equal negative 2xy minus 3y cubed plus 1 divided by x squared plus 9xy squared. And we have just found dy dx. Now, unlike other functions that are solved for y to begin with, when we take that derivative, the derivative is only in terms of x. In this case, because we had mixed terms to start with, we ended up with mixed terms here. So what that means is if I want to find the slope of the tangent line to a given point for the original function, not only do I need to plug in x into the derivative, I also have to plug in y. And if the function only gave you, or the problem only gave you x to begin with, you could find the y from the given equation. Remember, the point of tangency, when you're trying to find a tangent line for a function, the point of tangency resides on the original curve. That's the point of tangency. It's on the original curve. The derivative gives you the slope at that point. So again, we found our dy dx here. We could factor out a negative sign, but again, I don't think it's that much difference from what we've got here. So we just use implicit differentiation to find a dy dx. Why did we need what's called implicit differentiation? Well, the original function was not solved for y, so that meant we had to find the derivative of mixed variable terms here. And using implicit differentiation feels similar to the chain rule, especially when you're taking the derivative of those y terms. Okay.